In this topic, the methods for calculating the equivalent resistances for parallel and series-connected resistors are presented. In addition, the effect of internal battery resistance on the operation of a circuit is discussed. Another way to determine the current flowing in a circuit with resistors connected in parallel is to calculate their equivalent resistance. This can be done using the following formula that states that the reciprocal of the equivalent resistance is equal to the sum of the reciprocals of the resistance in each branch. In our example, then, we find that 1 over R equivalent equals 1 over 50 plus 1 over 100 plus 1 over 100 equals 0.04. Now remember, this is the reciprocal of the equivalent resistance. In order to find the equivalent resistance, we must divide 1 by 0.04, and this comes to 25 ohms. Thus, the current supplied by the battery is equal to 100 volts divided by the equivalent resistance, 25 ohms, which equals 4 amps. It checks with our earlier calculations. Now let's take a look at resistances in series. Here we have a 100-volt battery supplying two 5-ohm resistors connected in series. In this case, the total resistance is equal to 5 plus 5 equals 10 ohms. Consequently, the current supplied by the battery is equal to 100 volts divided by 10 ohms equals 10 amps. But what is the voltage drop across each of the resistors? In each case, we have 5 ohms times a current flow of 10 amps equals 50 volts. So we have a total voltage drop of 100 volts, which is equal to the voltage supplied from the battery. However, when performing this calculation, we should also take into account the resistance of the battery itself, in this case 0.1 ohm, and also the resistance of the conductors of this circuit. Let's assume another 0.1 ohm. So the total voltage drop through the battery and conductor resistance is equal to 0.2 ohms times 10 amps equals 2 volts. So this means that the current flow through our resistors will be somewhat lower than we had originally thought, and consequently less effective. This little digression points out the need to always ensure that connection leads have adequate current carrying capacity for the task at hand. Here is another example where we need to allow for the voltage drop through the resistance of the battery itself. The 100-volt battery is feeding 4 parallel circuits, each of 8 ohms resistance. Our first task here is to calculate the total current flowing in the circuit, and in order to do that, we need to find the total resistance of the circuit. The equivalent resistance of the 4 branch circuits can be calculated from the expression 1 over Re equals 1 over 8 plus 1 over 8 plus 1 over 8 plus 1 over 8 equals 4 over 8. To find the value of Re, we must turn this expression upside down. That is 8 over 4, and this equals 2 ohms. The total resistance of the circuit is equal to Re plus the internal resistance of the battery, 0.5 ohms. This adds up to 2.5 ohms. We can now calculate the value of current flowing in the circuit. That is 100 volts divided by 2.5 ohms equals 40 amps. The voltage drop through the battery is equal to 40 amps times 0.5 ohms. That equals 20 volts. This means that we have only 80 volts acting across the 4 parallel branches. From this we can calculate that the current flowing through each branch is equal to 80 volts divided by the branch resistance 8 ohms, and this comes to 10 amps. Therefore, the total current flow through all 4 branches is equal to 40 amps. This checks with our first calculation.